In the quantum dance of particles so small, a tale of entanglement begins to enthrall. EPR, Einstein, Podolsky, and Rosen, in their minds, a puzzle tightly woven. A pair of particles, once entwined, no matter the distance, their fates combined. EPR argued for hidden states unknown, a theory to challenge, a mystery to be shown. Bell's inequality, a test profound, to measure entanglement, the truth to expound. Inequality is breached, quantum realms collide, a dance of particles stretched far and wide. Quantum states, non-local and strange. EPR skepticism, Bell sought to change. Hidden variables or quantum delight, Bell's experiment pushed the boundaries of sight. Spin polarization, particles paired, Bell's theorem revealed what must be declared. No local realism could hold its sway, quantum entanglement and dazzling display. In laboratories, experiments unfold, EPR's challenge, a story retold. Bell's inequality, a measure so clear, quantum entanglement, a mystery dear. A dance of particles beyond our grasp, EPR and Bell and quantum leap, clasp. And quantum clasp. In the tapestry of reality, threads intertwine, a poetic physics where mysteries align. And I'll do that later. That was astounding, and I claim absolutely no credit to this. I mean, as you guys can probably tell, that was ChatGPT.
Yeah, save that one. It's. I don't know what to say.
It was just so good for typing 5 seconds out. That's great. But what are we actually? Who am I?
What is this? Yeah, what is this?
Like, what is
who are we?
All right, so this is Shen. That's me. And who is Shen? Well, your host, Rocket Man. This is SG2 on space, and this is episode 199. Since we did not do an episode last week, for those of you who are wondering whether you somehow missed it, you haven't. Leonard was out on break, and I was pretty busy, so it was fine. Speaking of which, I just mentioned the name Leonard without even addressing who that is. So let's bring him on.
Hey. What up, bro?
All right, just me, right? That's your name now.
Yeah.
Okay. Just Leonard, or Leonard Kramer, is a unique individual with a headband, as always. I like this design. I haven't seen it before.
Yeah, well, I mean, I match. I have a number of headbands, and I pick one every day, and so I get a shirt and a headband, and so when you come to my office, and you can just go to the receptionist and say, yeah, I'm here to see the guy with the headband, and they'll know who to.
Because nobody else, I'm sure, does that.
No, not really.
So for viewers from 10,000 years in the future, wearing headbands and a different shirt to work is not considered the normal fashion statement.
No, it's not. We need to communicate because this is a time capsule. This is a transmission to the future.
Exactly. So in the future as well, I'm sure people would have figured out what a lot of the topics we talked about. For instance, today. Oh, before I go on, let me just say, hopefully you're watching the show. Weekly Space Show, youtube.com/shinga/streams. Look up SG2 on space, or just go there, and then you will find on one of the playlists.
Yep.
Thank you to our supporters. And you can support the show on patreon.com/SG2 on space. I put here, thank you to Kyle Baker, Sam Welsh, and John Grace for the monthly donations. And oh my gosh, see, you get a kiss from Leonard. What could be better than that? Like that. A lot of things could be better than that, but that is pretty good. So I'll leave the ticker running on the bottom, so you could, everybody could just be like, hey, thank you to our supporters, patrons. Do need to mention Atum Ra, who was our producer for over a year. So eternally thankful for him. I'll leave this running. For now, let's go back and actually talk about what our episode is talking about, which is on Bell inequality EPR. For you who heard the poem, you may have gotten a general grasp of, okay, something to do with Einstein and something to do with quantum mechanics, but what is going on here?
Yeah.
So,
What?
Let's start from the beginning. Einstein did not fully like the concept of quantum mechanics, for what I
Yeah,
understand.
yeah. So I don't know how to. I don't exactly know how to begin with this to tell this story, but we have on this show we've often talked about quantum mechanics, and that was part of that was kind of the end story of an effort in the early part of the 20th century, like the first third of the 20th century, to understand what makes up reality, what makes up matter, what makes up things. And we came to this conclusion that when we make a measurement, that there's a certain level of uncertainty associated with it. And so what happened there was that all during the 20s, the group of all the scientists in the world were working this out, and they kind of hashed it out. And it came down to one of the scientists was named Niels Bohr, and the other one was um, um, Albert Einstein. Albert Einstein really kind of got quantum mechanics kicked off in the around 1905, along with Max Planck. But Niels Bohr, he picked it up and came up with a kind of notion that when you make a measurement of a particle, it fixes it into that state. So, for example, we have various kinds of things that we can observe about um, well, not just particles, but but collections of particles. Ultimately, what everything having to do with reality. So um, it got down to this idea that there is this thing called a wave function, and um, Bohr and I always get it. It's not sure. Heisenberg, Borg, and Heisenberg were a faction that came up with a notion that there was this equation that determined a wave function, and that when you make a measurement of it or it interacts with the environment, that wave function will collapse and produce a a certain um, uh, state of matter or state of the particle. So Einstein was not comfortable with this because he had this idea that nature should have um, that nature had to be localized, and so both ultimately what they ultimately
What does
well, yeah.
localized
So
mean?
it came down to this idea that when you have a certain kinds of observables with two particles that are together, they make up a single wave function. And so there are various kinds of reactions that atoms can exhibit. It could be a photon, it could be electron-positron pair, it could be different kinds of things that when they're created, they are coupled in a way that we now call entangled. And so when they're separated very far away, a measurement or an observation of one of the particles determines the state of not only the particle that you're measuring, but the particle that's remote, that's far away. And so the interpretation that Bohr and Heisenberg attached to that was that the state actually changed instantly at a remote distance. So you could take these two particles, and um, one of the things we've talked about before. We've talked about the dipole moment of an atom or an electron, the magnetic dipole moment, or the polarization of a photon. And a lot of people are familiar with polarized lenses, so that you can cross two polarized lenses and it will block the light. And if you take another lens, another similar polarized polarizer, and put it between the two, it will pass some light. And so that's a very mysterious, very strange kind of phenomenon. So the issue had to do with what does it mean when you make the measurement, and Einstein objected to this in 1935. There was a paper, and it was I think the title of the paper was something like, can quantum mechanics be considered a complete theory? And Einstein, along with his colleagues at the Institute for Advanced Study in Princeton, they argued that when you make a measurement on one of the particles, it cannot possibly influence anything having to do with the particle that's at the remote site. So
Why do they say that?
well, because as you know, he's Einstein, and so Einstein's the father of relativity.
So it
And
can't
so
travel faster than the
it
speed
can't
of light.
travel than the speed of light. So you can't send information or an influence faster than the speed of light. And so in particular, I think the case that it was like a thought experiment that they published in 1935, where they said, and in the case in that paper, he just had two particles with the momentum. He treated just the momentum and the position of two particles that were separating. And so he said, you know, you can determine the momentum of this one particle, and then that will instantaneously determine the momentum of the other particle. But he said that can't be, because that would mean that it would have to transmit some information instantaneously. After this, in the 1950s, people thought of other examples of this having to do with the polarization of light, having to do with the spin of electron pairs, and I guess in this case we're looking at photons, and so there you can see this.
But the essential story is the same, though, in that somehow knowing one, measuring one, you automatically know what the other one's at.
If you know what one is, then you automatically determine the other one. And actually in this particular case, this is a good one because you can see the math for the quantum mechanical state, where the state is that funny Greek letter psi there, and it's composed of four. There's two particles, right? And it's a composite, or it's a what they call a superposition of two states, where one polarization is up and the other one is sideways, and then the other one is sideways and up. So the combination of those two forms the state of the system. And that if you make a measurement of, say, particle 1, then that determines the state of particle 2, and the whole state is said to be collapsed. But what if the two particles are on opposite sides of the galaxy, right? So a measurement on one can't possibly influence it. But interestingly, Bohr didn't respond to that well, you know, and so he actually answered Einstein's paper with a paper a few months later with exactly the same title, and he declared that indeed that their interpretation was that indeed when you make this measurement, it does change the state of the other particle instantaneously, and it then the issue kind of like went to sleep for 30 years. In other words, I want to let me summarize, because I sense that I'm being a little bit scattered in my thinking and a little bit disorganized.
I wouldn't go that far.
So
there's a lot to cover.
Yeah, it's a lot to cover. So the issue is that you have two particles that are in this thing called entangled, right? Einstein and the community in 1935 didn't use that terminology, but it's clear that that's what they were talking about. It's what we call it today. We say that they were entangled. And they had this property that the process of their creation caused them to be correlated in the manner that we're talking about. So that if you measure up or down, you know, like the spin of an electron, of two electrons,
right. Yeah, like
up or down. If you select the z-axis, okay, then you have a direction, right? So I decide to measure the z-axis component, and I will get a number that's up or down. I won't get something in between. All right, and that's just a fundamental mysterious property of these observables. It has to do with spin and that's
basically the moment you measure it, you only get one value.
You only get one value. It'll be up or down, or we could say 1 or 0, or 1 or -1, something like that. And then but because of the nature of the construction of these two particles, measuring one determines the value of its sister particle that's remote, that's far away. And Einstein said that can't be, right? And I think, and like I said, I think that it kind of went to sleep for about 30 years. In the 50s, and even when I was learning quantum mechanics, which was not in the 50s, but it was in the 70s and 80s, we didn't. This question actually never came up. I think that in the undergraduate physics class that I took, this issue, which is really so interesting and essential to really what reality is, was never even addressed. And there was this kind of social, believe it or not, there was a kind of, and I've heard other physicists complain about this, that there was like a social stigma to asking this question, so what is really happening? What does it really mean? And it even got to the point where there's someone, I don't know if it's Feynman, but I have seen Feynman write this comment says, "We don't know. Shut up and calculate," right? Because
that doesn't sound like you're actually doing real physics if all you're doing is just do the math.
Well, I think that what would, and it's we've praised Bohr, as being like a really great guy and that kind of thing. But I do have this sense that he was sort of a bully in a certain respect, that he just was able to he had such his result was so important, and the force of his personality was such that he would say, "Look, this is just the way reality is. It's not a question that can be asked." Okay. And I guess I kind of bought into that for a while, and a number of people, when we were talking about it. But in recent years, in the past, I would say 15 to 20 years, we've started to have to worry about combining quantum mechanics with gravity, and we've talked a lot about black holes and event horizons and Stephen Hawking and that kind of stuff. And so we really do need to start worrying about what it is, what is the nature of reality. And so like I said, so in 35, that was the state of the science. They kind of gave up.
1935.
About 1935.
Yep.
In the 50s, I don't think in the 40s, well, everybody was busy in the 40s, what they were doing in the 40s. And then in the 50s, people were busy inventing transistors and lasers and doing all the things that you can do with quantum mechanics. So all this stuff that we're getting out of it. So it was all practical kinds of things that people were concentrating on. But there was one guy, his name was John Bell. I think he was from Ireland, who was thinking about this, and he came up with a theorem. So the issue is, for Einstein, all events are local, right? So whatever happens, if I make a measurement at one point on one of the particles, I'll get up or down, okay? And that will be completely independent of the other particle. So if I make the measurement of the other particle, I shouldn't get the same. I mean, it will be either up or down, but that was somehow a component of that was a property of the particle as it was transmitted. So before the particle got sent over to the remote location, it had that spin up or spin down characteristic. So it's just like, so the idea is like, okay, so the particle are two gloves, right? A right and a left hand glove, and they're like in a ball, and you take them apart. So one glove is right and one glove is left, and so you go off and you put it in a box, and you open up the box, and okay, my glove is left hand, so that means my partner has a right-handed glove. That's what Einstein said. Okay, Bohr said no. When you open the box to look at the glove, it becomes a left-handed glove. And
how is that possible?
Right. How is that possible? Well, Einstein said it's not possible. Okay. And And most of us think it's not possible. Okay, but
Yeah.
John Bell came up with a theorem, and we're not going to do the theorem tonight, but he came up with a theorem that because another thing that I'm not telling you is, like, for the example of a spin or for polarization, you can do a measurement of a particle on one side and get spin up or spin down in the z-axis, and then if you make a measurement in the x-axis, an orthogonal direction, it'll be completely random. It will not determine, that will not be determined. So the z-axis and the x-axis momenta, those spins, are they call complementary variables. You can't simultaneously know both of those. So that doesn't help, okay? But if you take the measurement at 30 degrees, right, then the correlation of the two particles, the influence of the up or down, then sends us, it's like it raises up a signal in the mathematics of probability. And John Bell, what he did was he wrote a theorem that explained what happens if we have these things called local variables, or sometimes you'll see the term hidden variables, that there's some kind of hidden variable, which is what Einstein was trying to promote. And so it assigns a certain probability if you're at 30 degrees, as some small angle away from the z-axis. So your z-axis is not 90 degrees, but something less than 45 degrees. Then the influence appears in the correlation. So you still get a random number, but it's correlated, meaning the number of times that you get a component in the z-axis is greater than it would be if there were local variables, that the way Einstein relates it. I know I'm not articulating this as well as I would really like to, but the result is,
Go
yeah,
ahead.
I don't really want to get into that very much, because I have trouble like following it myself, and I've really worked hard at trying to see it, but I don't. So it's like it's a very slippery kind of concept.
Does this actually mean anything to you?
Yeah, this is the whole thing here. And so what Bell is trying to say is, or what he has demonstrated, is that if there are local variables the way Einstein says, then the correlation at 30 degrees is smaller than what is actually observed. And that what is actually observed is consistent with Bohr's concept that when you open the box and look at the particle, it instantaneously transmits some kind of nature of reality to the other particle. And that's just the way it is. And so that was in the early 60s. That was about 1964 when Bell wrote this paper. It's not a very well written paper. It's written in an obscure journal that went out of business. And I don't think the paper was even noticed for another few years. So in the late 60s, about 69 or 70, there was a group at University of California at Berkeley. And remember, this is 1969, right? So it's like summer of love and hippies and I want to say all of my
people who wear headbands like yours.
Yeah, and so there was a group. I don't remember the names of all the people, but that was when it was like, okay, so a conscious observer makes a manifestation of something physical in the universe, right? And so that was a very appealing kind of very Zen sort of thing.
Mm-hmm.
And in fact, if you go on Amazon, you'll find all kinds of books like, the physics of Zen, or the dancing Wu Li masters, and that kind of thing. But there was a group there that found this paper and it kind of reignited the interest in the idea that, well, observation, and we'll talk about that if we get to it. But if you observe something, then you change it, right? So that's very Zen, very you know what I'm trying to say.
I know precisely
So
what you're trying to say.
I think that this group, and I don't remember all of the names of the people there, but they all recently got the Nobel Prize.
Nobel Prize, right?
In 2020.
Is it the? Oh, I was trying to find
Just
it.
recently, it's 50 years later, but so what they did was they figured out, they looked at this and say, we can test this experimentally, and they started collecting experimental stuff in the labs at Berkeley and put them together, and they've designed all kinds of experiments to actually test the proposition that the correlation at a 30-degree angle was greater than it would be if there were local variables, and so the reality violates Bell's theorem.
So what does that mean?
That means that very strange thing that Bohr said was happening is really happening. They had no way of testing it in the 30s, but in the by 1970 and 70 in the 70s, they had enough the technology had advanced well enough for them to be able, electronic switches and so forth, for them to be able to test this in the laboratory. And indeed, the influence, there is some kind of influence that is represented in the in particles that are separated, and that's where we are today with this.
So our point here is that this is how nature behaves, and there is no paradox.
Bohr was right. Einstein was wrong. There aren't any. There are no local variables, and this insistence upon locality, no matter how unpleasant that is for us to contemplate, it does not prevail in nature.
Higher values for the correlation between the results than it's possible through hidden variables.
Yeah, right? And it's significant. I mean, it's really quite significant. It's a significantly higher correlation. So are you all right? You still?
Yeah, this is
stunned
interesting
by this?
stuff.
Yeah.
It's just like
I told you. I think this is one of the most interesting things to relate.
This Alan Aspect was one of the ones who won.
Alain Aspect is one. I don't know exactly. I don't want to.
Alain Aspect,
Clauser
and Anton
Zeilinger. Yeah, and so that was so it was finally recognized. Groundbreaking experiments demonstrated the potential to investigate control particles that are in entangled states.
What happens to one particle in entangled pair determines what happens to the other, even if they are really too far apart to affect each other.
Even if they're light years apart. Okay, so now everybody's thinking,
wow,
does that mean that we can communicate?
Right? Does it?
Yeah, no. Why? Because the thing that you measure is a random variable. So you'll measure. So what it means is I'll measure like I'll measure 1 or 0. Okay, so I get 1 out. Okay, all I know now is that the other person sees 0.
0
on the other side of the galaxy. Okay, I have a 1 and the other person has a 0, but I can't control whether it is a 1 or a 0.
I see.
I can't force it to be 0 or 1. And so it's more like if I'm looking at it, I think I thought about it this way. In the old days, we used to have TV, and when you weren't tuned to any channel,
we still have TV.
No, we have like screens that we look at with high def, and it's digital and stuff like that. I'm talking about the real TV.
Real TV.
Real TV that when you would tune it to channel 3, okay, it was just static, right? And I'm not even sure that everybody's seen this, but maybe you have. You might have seen it in old TV, on old movies or something like that, where somebody's looking at static on the TV and it's just black and white lines, black and white dots on the screen. And so that's all random static, and actually some of it's coming from the cosmic background cosmic ray back, galactic cosmic ray, not cosmic ray. I always get that wrong. Cosmic microwave background. It's a little tail end of the distribution there, and a lot of it's just like from decay and different kinds of things going on all over the place, and just random noise. So it's like what you would see if we were looking at like a transmission. Then I can say, all right, I see this pattern, and somebody on the other side of the galaxy who's also observing an entangled state broadcast, like we're talking about, they would see static too. It would just be wherever I see white, they would see black. Wherever I see black, they see white. But they would see exactly the same pattern. But I can't modulate the pattern. All I can do is send static. I can't do anything to modulate it in order to send a signal. And that's just the way it is. And it's cool. So
really, this does not provide us a means of sending information faster than light, since it's randomized in terms of what
doesn't. Now, there may be some angle, but
Einstein had issues with it, and his colleagues as well had issues with it because of what? The faster than light kind of information.
The faster than light thing. He says that can't be, but I wish he was around. I wish he was around to be confronted with the evidence. He did. He only lived to 55, but it would have been nice for him to he probably would have been pretty excited by it. Actually, he would have been excited to be wrong about that.
Sometimes it's excited to be wrong about something.
Yeah, Bohr didn't live long enough either. Bohr only lived to be until I think 61 or 62, but so Heisenberg lived to 1972, I think. So, but I don't know if he was alert enough to be able to come. People were really publishing this in the late 70s. Late 70s, early 80s is when these papers started coming out about the effect. So anyway, maybe it seems kind of dull and boring to a lot of people, but to me it's pretty exciting. I just think it's a wild thing that
What was that scary? Yeah, I guess that's a little too close.
You're a little too close there. So the end.
Yeah.
What else you want to talk about?
Well, I mean, there's something I always want to talk about.
Yeah.
You're like, not sure about that part. Okay.
So that's the explanation. That is the essential story about quantum mechanics, that and that nature is like that. There is some kind of influence that's transmitted instantaneously, and it's real. But as far as so one of the things is, what is an observation? What is a measurement? And that's one of the problems that we've struggled with for a while. I actually don't think I think I understand. I think I have a resolution to the problem. Of course, we talked about many worlds, which I don't think much of. The many worlds hypothesis and so forth is that when you make a measurement, okay, when you observe something, what you always observe a particle or an event. So for example, if the photon is coming in and interacts with a CCD device to give off an electric signal, or more prosaically, photographic film. So the photon will come in and it will strike some of the chemical in the photographic film and change it into a little dot. Well, what has happened there is that the wave function has selected, and this is an essential mystery. The central mystery, and the main thing is that random things are going on. Nature does random things. You seem uncomfortable with that.
I'm muting myself. I've always known, I mean, nature does random things.
Yeah, so
But nature also selects something. That's what you're saying.
So somehow it selects where to go. So a particular photon, a particular grain of silver nitrate on the film emulsion gets selected, and that's an essential mystery. Physics fails to tell us how that happens. We only have probabilities. We can only deal with probabilities. And so what happens is that in the old days, we used to say that the wave function had collapsed. Okay, so well, in a very real sense, that I guess the wave function has collapsed, but it has interacted with the chemistry there. So now the wave function continues to progress as time progresses, but it's manifesting in different avenues. There's different possibilities and different probabilities. Some of them are much narrower than others, and so when you view the photographic film, you see that grain, and then your eye reacts to it. So it enters a state. It becomes part of that state. It influences your nervous system, which then assumes a certain state. And so that's all manifesting. That's the manifestation of what an observation is that a quantum mechanical thing has happened, right? A random event occurs, right? Then you interact with the result of that event, and your nervous system assumes, your brain and your nervous system assumes a certain state that's consistent with the photon striking the film at that particular point. And what an observation is what that feels like to you. So I've never seen anybody explain it that way, but I think that's the way that's what a measurement is. So that's a little bit off task from what we've been talking about, but yeah.
And I realize I'm muted again. So
I was trying to have a conversation with you while you were muted and to see see if you would notice.
I did notice.
Yeah.
So you're saying a large part of that, in terms of observation, is due to the observer.
So it used to be they thought that consciousness had something to do with it. In other words, that I mean, I'm not joking about this. That was the nature of the Copenhagen interpretation, and that's what I was taught, as an undergraduate. I said, so a conscious observer interacting with it makes a measurement, and then it assumes that state. But I argue that it goes into that state, and then you react to the photon goes in. Well, about the sleeping cat and the awake cat.
Schrodinger's cat.
Yeah, Schrodinger's cat. So, Schrodinger's cat is either awake or sleeping, right? He's not in a superposition, right? So what has happened is that we talked about this before, but just to background, there's a Schrodinger's cat, and Schrodinger, he talked about the cat being dead or alive, but it's always kind of brutal to me, So
asleep or alive.
So it's a sleeping gas, I think Sean Carroll, who's one of the YouTubers, he's also equally kind of repelled by that. I saw somebody else say that the radioactive decay will drop some food. It'll feed the cat or not feed the cat. So when you open up the box, the cat is either full or hungry. Right. Right. So there's different kind of things, but I'm off task. So what happens is when the cat is either asleep or awake, right? When the photograph. So what has happened is that the radioactive decay is a random event governed by a wave function that we can get our hands on, right? We can get our brains on. We can understand that. And then it selects, by this thing that we don't understand, it selects a particular point where it will then open the switch, right? And then the wave function is still there. It's just narrowly focused along a particular channel instead of spread out over many different paths. where there can be interference. So so we don't have any interference because the wave is sort of incoherent at that point.
Mm-hmm.
And then it goes in and it opens the sleeping gas, or not,
Mm-hmm.
depending upon whether it's happened. And then the cat then falls asleep, or it's still awake, right? So those two alternatives occur. And then when you open the box, you then become part of that system. So anyway, that's what I think. I don't think that there's anything. I don't think it's really that mysterious as soon as you start to appreciate the fact that you are also a quantum mechanical system, but that you're, like your macroscopic body, and that you're interacting with it in the same way. So I'm open to some challenges to that. People could write to me and tell me where I've gone wrong with that. So anyway, now there is another thing about determinism. So
I know we return to this topic quite a lot.
So one way to resolve a lot of this is if everything has already been determined. Okay, now keep in mind, I'm returning now to the entangled particles. So I make a measurement on one, and then I observe something, and then it causes something. We have this idea that there's some causal relationship, but what if there isn't? What if it is? What if the future exists just like the past, in the same respect that the past exists? And so there is
that means everything's already determined then.
Everything has already been determined.
That's what you're saying.
And that would explain it. It's not a very good explanation because it doesn't help us very well, to understand it. It's sort of, I mean, I'm critical of that, but for much of the same reason that I'm critical of the many worlds hypothesis. Many worlds hypothesis is the one where every time we have a quantum transition, well, the world divides, right? And so all of those possibilities exist in some respect. And of course, my criticism of that is it doesn't tell us which path we follow. So there's multiple, there's an infinity of paths. There's an infinity of me talking right now, although as I've pointed out, I'm having the best possible path through life.
I understand. You somehow know that part. Okay.
Right. But that doesn't help us understand anything. Maybe it's useful to think about that, to propose that, but it doesn't help because we need to decide which path we're following through, which universe are we following? And that's the same question of which photon or which particle of silver nitrate gets turned into a silver particle on the photoemulsion plate. So we don't know. We don't know the answer to that. We think that we've done a pretty good job with physics does tell us what the probabilities, managing the probabilities of all of these things, but we don't know. We don't have physics that tells us when a photon scatters from some event and lands somewhere else, and it does that random number generator thing. We do not know, and that's just the state of that's the way it is. That's the way physics is. But if everything is already predetermined, then we can understand instantaneous communication. Okay, so be interesting to find out what Einstein would think of that. Einstein would probably say, yeah. He must have thought about that, but I don't know that if he wrote anything down about it. So, the end. I think that's all I wanted to talk about. What do you want to talk about?
I no longer have anything worthwhile to talk about now that you talked about all this.
Well, I don't want to dominate the conversation. Well, no, that's not true. I like dominating.
You do want to dominate the conversation. That's been the whole thing. But it's okay because this topic a lot more about it than I do. I mean, I knew about some parts about EPR and not a whole lot about Bell's inequality, and you
Yeah,
explained it.
Bell's inequality. I've followed it through, and at a certain point, I get it, and then
You get it?
and then
You don't
I
get
leave it for a while, and then I come back and go, wait.
There's so what is it? There's a website.
A lot of there's a number of
see this.
videos. I mean, there's
This
an
one's a very
English
good one.
there's an English science popularizer. His name is Jim Al-Khalili. And you can go and he has a whole series of TV programs that I think he did.
Are you recommending it?
Yeah.
Jim Al-Khalili on what is
Jim
it?
Al-Khalili.
Bell's inequality.
Yeah, I think he's good.
I'm not necessarily going to promote somebody else's show, but
well,
if you want to look at it, here I guess I will promote his stuff. Here's his,
all right.
Okay, so what I'm going to promote is the Stanford philosophy website. You can read all that if you're a reader. Now, if you're a watcher, you can watch what Leonard Kramer or just me said, which is here. You can go to jamalkhalili.com. I think that's his name, right?
Al-Khalili. Yeah, that's him.
Yep. You can go to this website or his blog and
Einstein's nightmare. Right. I don't know if it was Einstein's nightmare or not, but
who knows?
Yeah.
You can read it yourself.
So I think he's a good physicist and a good educator. So, and he's
all right. Great. Yeah. Okay, everyone. So with all that, I don't have anything more to add. What?
We're not going to talk about your favorite subject, or?
Sure, we're going to talk about our favorite subject. All right, let's see what we're going to do. You want UFOs videotape from airplanes, or series of videos of aliens in Australia?
I don't know.
I mean, which is better?
I don't know. You'll have to decide.
Okay, I'm gonna go with the first one. So let's go with that.
My friend.
Let's see how this works. Let's see how this works.
Oh,
what is this? Okay.
It looks like the wing of an airplane.
So this is from I don't know.
What? Oh,
UFO film from an airplane over Orlando. Do you see anything? Yeah, you do. Those 3 dots. 3 dots.
Yeah, I think it's a reflection from the glass in the window.
No, they're changing. It's something unknown and mysterious that you can't explain. And look at that. That doesn't make any sense. Like, what is it doing? It's just rotating around and it's drifting apart again. This is crazy. So don't tell me you haven't seen anything weird out of airplanes at times, maybe.
Well, other than just being in the airplane and
look at that. Look at that dot go. That's not a reflection. That's just something crazy is going on.
I don't know.
And then let's see. Here's another one. Caught from a plane over Canberra. I guess that's in Australia, right?
Yeah.
So, let's see what happens there. Oh, you see that? You saw that thing? That thing was moving so fast.
No, I didn't see anything.
Here, let me go back.
You know, my eyes are not as good as they used to be.
Here, let's try this again on the far left side. You're gonna see it. I went back a few seconds. Yeah, you see it? You saw that thing scuttle underneath?
No.
Okay, one more time.
Oh yeah. Was that it?
Wait, did it just happen?
I don't know. Okay, whatever.
Okay. Well, you can catch it later. I already replayed it. Oh, see? Okay, slow motion.
Oh yeah, there we are.
Yeah.
Yeah, what is that?
Don't know. See? Unidentified. I'm not saying it's aliens, but
it's aliens.
I mean, what could that thing be?
I don't know. It looks like an aspirin.
Yeah, so that's from a commercial airplane.
Yeah. That's pretty wild.
Then number 3, let's see here. What is this? Okay, be a little faster here.
Just a month ago, is it?
Airplane window, Massachusetts, 2013. Let's see what this looks like. This is like something I would do, right? Like look out the window, since I always like window seats, and you never know where you might see.
Well,
So look at that.
Oh, that looked like what was that? Yeah, I saw it. There's a plane, obviously, but
there was something else too that had
left
no contrails and just went really fast.
Yeah,
which was, yeah.
I don't know.
So
could have been a balloon, because a balloon could just, if a balloon were just there, then the plane could fly right by it.
This one.
I'd hate to think there's balloons up there that the planes could crash into. So,
don't know. Let's see here.
Maybe it was a Chinese balloon. Remember?
Then 2 UFO from. Okay, I'm not sure where that is. I guess the bottom got cut off. Yeah, I'll check it out later. And then what? Do you see it?
Yeah, I saw that.
What did you see?
The bottom? I just saw a little. Yeah, I saw something down there.
Yeah. That thing.
That I'm not so impressed with. I'm thinking that's like a lake down there, and the sun is shining. Oh wait, it's in front of the clouds.
No. It's not. It's actually. It actually like goes like through it. So
yeah, and it's moving at the same rate as the plane.
Now, let me see.
I don't know.
Yeah. So I mean, okay, and then this last one, 2015. I mean, you can clearly see whatever that was.
Yeah.
And that seems to be like near either takeoff, something.
Yeah.
So it's pretty crazy.
I guess it. I don't know. Right. These are actually pretty compelling. Except that why don't we ever see like really clear pictures of something instead of it's always some kind of fuzzy.
Okay.
Oh, her again.
No, it just ends with this random person saying, "Oh, go visit this website."
Oh, okay.
But you see, we don't know what it is.
We don't know.
It's a great mystery.
Yeah, just like random stuff that quantum transitions and the non-locality. This whole topic we were talking about, it's actually called non-locality, and it's a real thing. And there's nothing we can do about it. It's just that's the way it is.
Matthew says aliens in Australia. Yes, aliens are everywhere. Don't you know that? I mean, okay.
Is Matthew in Australia? Where is Matthew?
Matthew's not in Australia. He's a friend of mine. He's in Houston.
Oh.
But
okay.
Hi, all these sightings around the world, Matthew and anybody else watching, it is, weird phenomenon is everywhere.
Yeah.
It's not localized to one place.
Yeah.
So, I mean, look at like a guy wearing a headband.
Yeah, I was just about to say that. Yeah.
You might think it's localized to Houston, but it's not.
Yeah.
Anyways.
I'm having such a great time. So,
all right.
Thanks for letting me participate.
We are hitting 53 minutes live. Okay. This is getting too much.
Okay. So yeah, that's right.
I'm going to say, hey, thank you everybody for all that watching and stuff, and supporters and patrons, Kyle Baker, Sam Welsh, John Graves, and my producers, reviewers, Atum Ra. And anyways, you can go to patreon.com/SG2 on space. And with that, all that other stuff said, you can go youtube.com/SG2/streams, look up SG2 on space. We will most likely be back next week. We'll let you know what our upcoming schedule is on all. Just keep tuned.
Next week will be number 200.
Because
this is 199. Yeah.
I know. You can't count. Yeah. All right. So what is it? Namaste.
Namaste.
Okay.
Good night, people.